And we're rolling. Hi there. So today we're going to have a builder. So it's a set 2 because I've made a previous video with regards to this MATLAB programming, but um, the previous video has different concept. So now we're going to tackle. So if you hadn't watched it before, you could watch it because it would be a great help for this skill builder number 2. So in this video, what we're going to learn is first is we're going to find the Z transform. Second is complex valued signal. So we're going to handle that part also. And lastly, the difference equation. Okay, so this three topic is under digital signal processing, and this skill builder would be a great help with regards to this concept, especially in specifics of MATLAB programming. Okay, so before we start, we're going to begin with a great quotation from Steve Ballesteros. So it says that to give yourself the best possible chance of playing to your potential, you must prepare for every eventuality. That means practice. Okay, so what would be the three things that we will code for today? So the first one would be this, second one would be this, and the third one would be this. Okay, so let's begin with our first code. So the first code or the first problem would be using MATLAB, find the Z transform of x of n is equals to n use of n. Okay, so how do we start that? To begin, we should initialize. So it should start with a good initialization. Okay. Symbol capital X for our Z transform X, N, and Z. Okay. So we're going to again. This is just an initialization. N times fun N 0. So I've used step fun in our previous skill builder. So if you hadn't watched it, you could watch it so that you could have an understanding with regards to the step fun. Okay, so just a brief. So n would be the range of the step fun or this one, and also because step fun is just a unit step. So step fun is just a unit step. Okay, so and let's go for the important part. Okay, so again, so we're having this initialization because of our problem and use of n. So use of n is the step fun in MATLAB programming. You could also initialize it using ones. So you could also use that, but I prefer to use step fun. Okay, so again for the important part, so x is equals to ztrans, and then x. Okay, so that would be it. So that would be the programming for finding the Z transform for the equation of x. Okay, so let's evaluate this and let's look at our command window. So as you can see, this is the Z transform of x or of this one. Okay, so you could try and solve it to verify, but you could have just trust me on this one. Okay, so on the second B or the letter B, if you're up for challenge, so we'll use MATLAB for to find the Z transform of y's of n, and instead of n, we're going to square it and then use of n. So as you can see, we will just change this. We're going to change this since it's y. Okay. So y, shift enter, and y, shift enter. Okay. And we're going to raise it to or square it because we're just following this one. Okay, so the answer would be like this. So let's see. Okay, so I'm going to evaluate it now. Okay, so as you can see, this is the answer. Okay, so let's see into the answer. So as you can see, um, hmm, okay, so as you can see, z, if you distribute that, you will get the numerator, and then if you expand this, you will get this one. Okay, so we're done with our number one. So what we're going to do next is we're going to solve for the number two. Are you ready? Okay, so let's begin with the number two. Okay, so the number 2 would be this one. So it's a complex valued signal. So we should generate this one using this given with a range of -10 to 10. Okay, so we're going to plot its magnitude, real and imaginary part. Okay, so let's begin. Let's begin with initialization again. Okay. So initialization would be n is equals to the boundary that is specified in our problem, -10. Okay, then 10. That's it. And in with regards to this exponent, with regards to the exponent, -0.1 plus 0.3, we're going to place the j after the 0.3 in the MATLAB so that we wouldn't encounter the error. Okay, so I'm going to set this into or equate it into letter A so that the code will be much cleaner. Okay, -0.1 -0.1 plus 0.3j. Okay, that's it. Okay, so that's our initialization. Also, we're going to initialize the x, our function. Okay, so far so good. Okay, so we're going to use the subplot. So since we're going to have 3, 1, 1. Okay, so that's our subplot. So this is the important part, stem and the range, and then extracting the real part of the function of x. Okay, so that is our important part. Okay, so let me put a comment here. Okay, so that is our important part. So we're going to label this one. So the label would be this. Okay. So we're going to try to evaluate this to see the real part. So that would be the real part. Okay. So we're going to plot now the imaginary part. Okay. It would be just the same. It's also the important part, so take note. But we're going just to change that into imag. I've already made a video of this, so you could also check it out. Mhm. Okay, so that's our code for the imaginary part. Let's try to run this. Okay, so that's it, the imaginary part. Okay, and for the third part would be the magnitude part. Mhm. So just subplot. Let's just change it. And the same. It's also the important part. So as you can see, there are three important part here. So take note of those and also pay extra attention for those part. And this is for the label. Okay. So far so good. So let's try to run this. Okay, so that's it. So this would be the real part of our equation, and this would be the imaginary part, and this would be the magnitude part. So we've already made the second one. So let's go for the third part. Okay, so we're going to erase this. Okay, so first let's understand the problem. Okay, so given the following, so this is a difference equation. Okay, so this is the function of y, this is the function of x. So the first part would be calculate and plot the impulse response of h of n at this boundary. Okay, so as you can see, we're going to have or find the impulse response using this difference equation. So um, tips, when you're encountering impulse response, you should have or use the impz function since we're looking for the impulse response. Okay, so let's go and try this one. Okay, so initialization. Okay, so the boundary -20 to 100 as stated in the problem, and b is equals to 1. I know you have questions, but hold your horses. Okay, 1, -1, 0.9. Okay, okay. So to further understand this one, so let's look at the problem. Okay. So as you can see, the b symbolizes for the x. This one. So this is for x, function of x, function of x, and a is coefficient of y. So as you can see here, so 1, -1, and positive 0.9. Okay, so to further understand this, I've made some presentation with regards to this one. So y, a, and b, because the general form of linear constant coefficient difference equation is this one. So as you can see, a stands for the y, so that's why we've chosen this one. Okay, and the b is for x. Okay, so let's follow the standard, because if also we're going to use it in imps, so we're also going to use this one, b and a, where b is the coefficient, but this one it's from the denominator and numerator. But nevertheless, so what my point here is that the a stands for coefficient of y and b is the coefficient of x. Okay, so that's our initialization part. Okay, so let's go for the important part. Okay, so the important part would be this one. Okay. Okay, so since this is an important part, I expect you to pay an extra attention for this one. H is equals to impz. Okay, so b, a, and n, the range. Okay, so n stands for the range. You could also just put a number here, 40, but that would be from 0 to 40. But since we're dealing with, or the given, or the requirements from -20 to 100, we're going to put it here. But again, you could just also put number. It would be start from 0 to the number that you've selected or inputted. Okay, so this again is the important part. So after that, we're just going to plot the output. So the output would be we're going to use the subplot, and then a stem to plot this one. Okay, and the title, and then the label. Okay, so far so good. Okay, so let's try to evaluate this one. Okay, so this is our h of n, and this is our impulse response. So we're done with letter A. We've finished the calculate and plotting the impulse response from -20 up to 100. Again, we've just used the impz function. So we're going to letter B. Okay. So for letter B, we're going to start with initialization again. So this is for letter B. Okay, and this is for A. Okay, so what would be the problem? The problem is calculate and plot the unit step response. So with this one, we're going to use the filter function. Okay, and we're going first to define a unit step. Okay, so to define a unit step, I've already discussed it in the previous part. The range, -20 to 100, and then 0 because it's a unit step. Okay. Okay, so again for the important part. Okay. So the important part is this is the unit step response, and to get that, B, B, A, and then X. So that would be the unit step response. So that would be the calculation of that. Okay, so we're going to the plotting or the output. So it would be this one. So as you can see, I used the subplot again, and then stem outputted the S, which is the S is our what? Unit step response, and we use filter function, and then label so that it would be neat and clean. So let's try to run this. This one. So as you can see, this is our step response. Okay, so the third question would be, is the system specified by h of n is stable? Okay, so there are two methods to find this. So the first one would be finding the roots. Okay, so let me do this. Okay, so see. Mhm. Roots A, and then after that we're going to find the absolute value. Okay. Okay, so this is the condition for that. Mhm. Okay, so let's try to run this. We're going to clear this first. Okay, so let's run this one. Okay, so as you can see, when you run the code, so the result would be this one. So what does it implicate? Does it implies it's stable or unstable? So we're going to look for the condition. The condition would be this one. So if z, the one that we've computed, is lower than 1, therefore it's stable. Okay, so as you can see, it's lower than 1, therefore it's stable. But again, I've said before that it should have, or there are two methods to approach this one. And the second method would be using a visual inspection, and we're going to use the z-plane. I've already have a video with regards to z-plane, so you could also check it out. So you will have more understanding with regards to this one. Okay, so what is the result of this? The result of z-plane would be this one. So as you can see, the poles is inside the circle. Therefore, what? Therefore, it's stable. As long as it's inside of the unit circle, we could consider it as stable. Okay, so that's it for today. And today you've learned how to solve this one. So Z transform, and then complex valued signal, and also dealing with the difference equation. So if you've learned with regards to this one, so with the skill builder number 2, okay, so you could give it a thumbs up, and also subscribe for more videos. Okay, so that's it. I'm Jerome, and have fun. Bye bye.